record.
Right, so welcome everyone to the first talk of the 2024 edition of GROOT. Today we'll be hearing from Jack Romo from Leeds, University of Leeds, on homotopy categories, homotopy bicategories, infinity two bicategories. So take it away, Jack.
All right, thank you very much. And first off, massive thank you to the organizers for setting up this event. I've seen some really great talk titles coming up. I'm excited to see what's in store soon with GROOT, and a huge shout out to GROOT, of course. This wouldn't have been possible without him. All right, so, but of course, enough platitudes. We're mathematicians, we're interested in problems. And today I want to talk to you about a particular problem that I have. Imagine, for the sake of argument, that you're a higher category theorist. You study higher categories, you collect them, you observe them, you display them for your guests on your prize shelf. And in particular, as a higher category theorist, you might take an interest in something called an infinity, n category, an infinity n category. Now, as you know, as a specialist in higher category theory, an infinity n category consists of a few things. In it, you'll expect to find objects, morphisms between your objects, morphisms between the morphisms between objects, morphisms between the morphisms between the morphisms between the morphisms of objects, and so on and so forth, all the way up to infinity. However, the comma n bit tells us that, for instance, in the case n equals 2, all of the morphisms above level 2, level 3 and up, will be equivalences. Okay, so you have your infinity n categories. You have some guests over, crack out the wine, your partner rolls their eyes as you pull out your shelf of prized infinity n categories again to display. But one of your clumsy guests decides to pick one of them up, and it crumples like an autumn leaf in their hands. All of the n+1 morphisms, n+2, and so on and so forth, collapsing down into mere path components. When they drop it before you, you see that you no longer have an infinity n category, but merely an n category. You politely but firmly ask your guests to leave, and you ponder this situation, this problem. How could this have happened? You know this is a problem because, while it seems simple on the outset, in higher category theory, nothing is quite so simple. There are many models of higher category that we have to think about, and at no point in this whole discussion have I mentioned what models of higher category we're using. Indeed, higher category theory follows a slightly reverse path to the rest of mathematics. In usual math, we start with definitions and prove theorems. In higher category theory, we start with theorems and seek definitions. We want certain things to hold of higher categories, the homotopy hypothesis, coherence theorems, the periodic table of monoidal categories, and so on and so forth. And we seek definitions that satisfy these desiderata. Of course, as one might expect, there are 200 going on 201 different definitions, and the complexity of this problem will depend on what models I'm choosing. What kind of infinity n category am I starting with? And what kind of n category am I going to? Of course, we're going to choose the hardest possible case because that's where the most interest lies. We're going to pass from what I'm going to call, so we start with some notion of infinity n category, going to some notion of n category, and we're going to start with what I'm going to call non-algebraic models. And we're going to go to what I'll call algebraic models. Now, why do I call these names? Well, in a general higher category, if you have a chain of morphisms like this, for instance, which you can expect to have, you would want to know, for instance, what the composite of these three morphisms is. And algebraic or non-algebraic models, I give them these names because they have different answers to this question. In an algebraic model, you would expect to find a particular composite of the three morphisms. But you'd also expect to find other composites. For instance, you might get another one, so this is just composing all three at once. You might get another one, which is composing the first two first and then the last one. Or you might get another one, I guess I shouldn't put these as actual, well, in any case. Or you might get another morphism, which is composing the last two first and then the first one. Or maybe you'll get yet another one by composing these first two and then putting an identity here and then composing another one, composing these two, right? And so on and so on and so forth. And there are all these different composites that you'll get just by, continuously applying these operations freely. Between these, you'll expect things like associators and uniters, which you might have seen from bicategories, two isomorphisms at level 2 that equate different composites. But then between those, you'll get two-dimensional holes, which get filled by things like pentagonators, if you've seen those in tricategories, and so on and so on and so forth. And in the end, you get this big space of different composites with higher isomorphisms and higher equivalences between those. So this answer, where we know what the composite is of a bunch of morphisms in a certain manner, these are algebraic models. And so, for instance, we'd have things like bicategories following Bénabou. We'd have classical tricategories. We'd have more, perhaps less well-known models, such as the Batanin and Leinster models of n categories for all n. We'd have Trimble n categories, and so on and so forth. There are several of these models. The idea is that for a chain of morphisms, you should know how to do the composition. You have operations that do composition. Now you might look at this and think, God, this is a terrifying picture. There's all this like increasing complexity going up into higher and higher dimensions. And you'd be right to think that. It is hard to write down what an n category is. That's the whole challenge. So on the other side, you might decide, well, actually, I don't really care what the composite is. All I know is there are a range of morphisms that could be the composite, and that they're all equivalent to one another. They're all just equivalent to one another. In particular, all these different possible composites and the equivalences between them form some kind of space, some kind of homotopy type, a topological space. The different composites are points. The associators and uniters are paths, and you get surfaces in higher volumes. And all what we'll specify is we don't care what all of those are, just that this space is contractible. So we don't know what the composite is. We just know that all possible choices are equivalent to one another. And if you do this, then you get these so-called non-algebraic models, where you sidestep all of this complexity and turn it into homotopy theory, because you see this as a space now. So we get things here like complete n-fold Segal spaces, Segal n categories, quasicategories. They do admit an interpretation like this. It just takes a little bit of thinking. And things like complicial sets, and so on and so forth. There are many, many models here. Okay, so why am I interested in going from a non-algebraic model to an algebraic model? Well, the point is that we're going from a situation where we don't know what the specific composites are and what the associators are to a situation where we do know. This is almost analogous to starting with a vector space and picking a basis. But we're trying to find all of this algebraic structure in a way that's coherent. And in doing so, we will be forced to extract all of the information that's implicit in the non-algebraic models. This is going to be painful, but it's a growing pain as far as I can see. This teaches us more about how these two situations relate to one another and could potentially help us bootstrap results in the algebraic situation from the non-algebraic one. The non-algebraic one has seen a lot more progress in recent years because it builds on homotopy theory. Okay, so that's what we're going to try and do. And in particular, for us, we're going to be interested in the case n equals 2. We're going to use complete two-fold Segal spaces. I'll say what those are. And we're going to go to bicategories. That's what we're going to do today. Okay. Now, I should admit up front that I'm not as original as I might think I am. There are quite a few approaches to analogous things. So for instance, Campbell went in this paper from two quasi-categories, another notion, another sort of non-algebraic notion, to Tamsamani two categories. And then some work by Lack and Paoli allows you to jump from those to bicategories very nicely. Another piece of work was by Moser, who showed how to go from double infinity one categories to strict double categories. And this restricts to going from complete twofold Segal spaces to strict two categories. And there's a nice equivalence there. And then this paper compares many of these different approaches with one another. So you might wonder, all right, well, with all these different approaches in mind, why bother doing it again? The reason that I want to talk about this today.
Can I ask a quick question?
Yes.
So from my understanding of those, in other papers, those papers that you mentioned that you usually consider like the nerve in the opposite direction. So is this these functors that you're considering like adjoint to those?
Yes,
like
exactly. Yes, they are. They should be equivalent adjoint, actually. Yeah, yeah. Cool. Good question. All right. So why are we doing this again? And there are two reasons. One of them is that there is interest in doing a pointwise computation. A lot of these approaches, Campbell's excluded, do a very high-level approach, which don't necessarily tell you exactly what the bicategory is, or are satisfied with going to strict ones because they're equivalent to bicategories. But there is interest in going to specific bicategories, for instance, comparing results in the infinity 2 world and TQFTs to results in the bicategory world of TQFTs. There's also, in the approach that I'm going to show you today, I think there's this approach is kind of intriguing because today we're going to see how to obtain all of the coherence isomorphisms, so associators and unitors and such, and the conditions on them, such as the pentagon condition, from the infinity 2 category directly. So from the infinity 2 category directly. What I mean by this is that we're going to identify within a complete twofold Segal space certain lifting problems. The solutions to these will be composites. Homotopies induced between them will be the coherence isomorphisms, and higher homotopies between those will be the coherence conditions. So this will very directly show how the algebraic data results from this contractible space of composites interpretation. Okay, and I want to talk about this because this is, I believe, in my opinion, that this sort of approach is not just restricted to level 2. There is no reason that it should not extend to level n and to various other structures, such as symmetric monodal structures. Okay. So, right. The first thing that I need to do is tell you exactly what I mean by a complete twofold Segal space. Now, I'm going to omit some technicalities here. We don't need everything. I just want you to have the ideas of what's going on here and enough for us to do the constructions that we're going to do. Okay, so I don't know whether everyone here is comfortable with simplicial sets, so I'll do a quick little whirlwind tour. Okay, simplicial sets. The idea here is that we're going to have some sort of what you might call a combinatorial model of homotopy theory. And I'll just briefly say what the interpretation should be. So we'll have this category delta that we'll start with. And delta is going to be these sets, so ordered sets of n plus 1 elements for all n greater than or equal to 0. Okay. So what are these elements and how should we interpret them? Well, we're going to interpret each of these as kind of like oriented tetrahedra or triangles in higher dimensions. The idea is that level 0, this just has a single element, and we're going to interpret that just as a single point. When you look at 1, we have 0 is less than 1, and we'll interpret this as 2 points and the less than relation as an arrow between them. The ordering gives us an order on these arrows and such. If we look at 2, we'll interpret this as we have 0, which is less than 1, which is less than 2, and 0 is itself less than 2. And so we can interpret this kind of like a triangle, like this. And 3, just to quickly show, I won't say too much other than just if you look at everything, you get what you might consider a tetrahedron. And this continues. This interpretation is totally fine in higher dimensions. Okay. The idea is that a simplicial set will just be a functor from delta op to sets. It's a pre-sheaf on delta. And what is pre-sheaves but co-completion, right? So we can interpret a simplicial set as just a bunch of these pictures glued together. Yeah? Ooh, intercom. How's that sound? Okay, in any case, simplicial sets, you can kind of see them like an extension of simplicial complexes. They kind of look a bit like CW complexes as well, but they're a combinatorial model of topological spaces. And in a very precise way, they model homotopy theory. You can convert topological spaces to simplicial sets, and you can do homotopy theory in them. And in particular, you have a specific case of simplicial sets called a Kahn complex. If you have a Kahn complex, this is a special simplicial set where, for instance, if you have a diagram like this, which is a chain of two paths in our topological space, so to speak, we identify such a diagram, then we can, in some sense, concatenate these two paths. And what do I mean by that? Well, I'm able to find, whenever I have a diagram like this, a chain of two arrows in my simplicial set, I can find a diagram like this that extends the original one. So, and you can do this in higher dimensions is all I'll say. So you can always concatenate paths, you can concatenate surfaces and so on and so forth. This is what you'd expect of a topological space. So, Kahn complexes look like topological spaces. There is an interpretation of, or there is a statement that one can make in higher category theory, another desideratum that I might have mentioned the name of, the homotopy hypothesis. Given a topological space, we can obtain a particular higher category, what we might call an infinity groupoid, which is to say an infinity zero category. Every morphism is invertible in a weak sense. From a topological space, we can obtain an infinity groupoid by having the objects be points in the topological space, having the morphisms be paths in the space, having two morphisms be surfaces, three morphisms be volumes, four morphisms be four-dimensional volumes, and so on and so on and so on. The homotopy hypothesis claims that this obtains all infinity groupoids, that every infinity groupoid can be interpreted as a topological space. The theory of infinity groupoids should be the theory of topological spaces. What I'll say to that end is a declaration. Kahn complexes, implicitly replacing topological spaces with Kahn complexes here, model infinity groupoids. And the reason that I say declaration is because in some models of infinity groupoid, this is a theorem. In others, this is a definition. So depending on what model you're using, there are models of higher category where they prove the homotopy hypothesis as a theorem. It's not assumed. And there are other models where they assume it. So you can just have infinity groupoids for free. Infinity zero categories. Okay. So the interpretation here, just so I have it here, is that if we have a Kahn complex X, X0, which is the image of zero, the zero simplex, we should see this as the set of objects. So pictures like this. X1, we should see as the set of morphisms. So pictures like this. X2, there are two ways we could interpret this. One of them is to say, well, this is just the two morphisms. But a more useful approach for us today is going to be to see this as the set of, so either we could say two morphisms or compositions. That is to say, if you see a two simplex, you can see this as, hey, I've got a chain of two morphisms. I have F, I have G, And then I have a composite GF, and I have some two isomorphism witnessing the composition, right? In a topological space, F and G would be paths, GF would be some concatenation of the two, and this middle bit would be a homotopy witnessing the concatenation. Maybe you would have to shift, maybe the homotopy shifts the parametrization around or something. Okay. And so on and so forth. In general, we'll see Xn as composites of n morphisms. So, with this, that's not how you spell we have infinity zero cat. And the idea is we're going to bootstrap from this in order to get infinity n cat. We're going to assemble a bunch of infinity groupoids together to look like an infinity n category. That's the idea. How we're going to do this is we're going to get infinity n categories by induction. Okay. So suppose for the induction, we already have infinity n minus 1 cat. Then, for the sake of argument, suppose x, some x, was in fact an infinity n category. Suppose we have one. Well, there's a lot of things we can expect to extract out of X. And what we're going to do is we're going to identify some structures X should have, some conditions that structure should satisfy, and then declare that actually any structure satisfying those conditions already is an infinity n category. So that's the sort of argument we're going to follow. All right, this is all interpretation and intuition. These are not theorems. An infinity n category, we're defining that here, right? So if we had an infinity n category for sake of argument, let's reinterpret n, that set, as a category itself from 0, a category of chains of a chain of length of n morphisms, n plus 1 objects, right? Then we're going to extract a functor, which we'll also call X, from delta op to infinity n minus 1 cat. What we're going to do is we're going to send n, this chain of length n, we're going to send it to the infinity n minus 1 category of functors from n into X. This is our interpretation. Now, as part of this interpretation, these are weak functors, right? So an element of this would be in X, a chain of length n of n morphisms together with a composite and some isomorphism witnessing the composition. So X0, so functors from the 0 thing into X, just a single point. What this is going to be, remember this is an infinity n minus 1 cat, so this is going to be the underlying infinity n minus 1 category of X, where we removed everything that's non-invertible at level n. X1 then, which is functors from just the arrow into X, what we'll interpret this as is the infinity n minus 1 category of morphisms. X2 then, this becomes a little bit more interesting. We'll interpret this as the infinity n minus 1 category of composites. So diagrams like, composites, diagrams like this, where we've got two morphisms, F and G, a composite, and some witness to the composition. And so on and so forth. We'll see Xn as the infinity n minus 1 category of composites of n morphisms. Okay. So if we do have an infinity n category, we should expect a functor from delta op into infinity n minus 1 categories. This is the structure that we're going to expect. Moreover, this structure should satisfy some properties. Let's consider the following diagram in infinity n minus 1 categories. We have xn. Recall that we're interpreting this as diagrams like this, right? I should also mention very quickly, the fact that this is functorial and works in morphisms, we interpret this as pullback by precomposition by maps in the first parameter, right? So we get maps from x1 to x0 by obtaining the source and target of the morphism, for instance, and the degeneracy here, the identity, right? And these would be the two morphisms in the composite. These would be composing with identities, right? That's our interpretation here. Okay, just thought I'd quickly mention that. So back to this point, we should expect some structure from this functor from delta op and infinity n minus 1 cat. So consider xn, infinity n minus 1 category of composites of n morphisms. And now let's look at this, which is x1 pulled back over x0, and then another x1 pulled back over x0, another x1 pulled back over x0, and x1 again. This is again an infinity n minus 1 category. They're preserved by pullbacks. And we should see this as the space of chains of length n without a composite. And what this morphism is, what this map is doing, this downwards map, is it's forgetting the composition. Now, I mentioned before with this non-algebraic interpretation that for any chain of morphisms that can be composed, the space of possible composites should be contractible, right? Now let's make that precise. Let's pick some particular chain of morphisms. It's from, let's call this, we're picking out the morphisms from F1 to Fn. I'll write this a bit more clearly, actually. Just one second. This is a singleton, just a star. And this picks out a chain, F1 to Fn. Let's look at the pullback, the fiber over this chain. What this is, this space here, we see as the space, the infinity n minus 1 category of composites of F1, F2, all the way up to Fn, just all the possible composites. What we want is that this thing is contractible. Now, what we can say in order to make that more precise is that this should be an equivalence, this map. It should be the higher category of composites. It should just be equivalent to a single point. So the way that we're going to make that happen, the nice way and sort of the homotopy-theoretic way of saying that is that this map should be a trivial fibration, right? So what a trivial fibration is, the way you can interpret this is that the fiber over every point in the codomain is contractible. That's a way to see it. Contractible also means non-empty, right? Okay. So that is to say that xn to x1 by x0 by x0, x1 should be a trivial fibration in some sense. Trivial fibration. Okay. Well, actually, as far as I'm concerned for this talk, we're kind of done. This is roughly the definition of an infinity n category. Let me try and gather all of this together again, and I'll emphasize some places that I've missed out. So our definition of infinity n category is going to be the structure that I mentioned. Yes.
So this model looks a little bit like what Bergner and Rest do, like with a simplicial objects in some infinity n minus 1. Do you not have like completeness condition here?
Yes, that's something that I omitted that I'm going to mention. So I also omitted reedy fibrancy. So there's a few conditions that I missed out here. But these are the ones that we care about for the purposes of this talk. Okay, so a complete n-fold Segal space a complete n-fold Segal space is a functor x from delta op to into complete n-1 fold Segal space. It's equivalent to say this, that's fine, by fibrancy, basically. Such that, first off, the thing has to be really fibrant, which I am not going to discuss here. It's just to make those maps vibrations. Like you don't have to worry about it here. It's a technical condition. The important one that's of interest to us is that xn to x1 by x0 by x0, x1, we call these the Segal maps. This is a trivial fibration. And what do I mean by a trivial fibration more precisely? Well, if you do this properly, then at each step in the induction, you develop a model structure. So a homotopy theory. For those who haven't seen model categories, it's the enough structure to do homotopy theory in your category. You develop some model structure where the fibrant objects, what were once con complexes, are now your infinity n categories. And with that comes a precise notion of what you mean by a fibration. They're inherited from con complexes, though. They're not too weird. They're the weirdest things there, but they're not too weird, if that makes sense. And then plus a final condition, which is completeness, which I won't say too much about. All I'll say is that if you look at this induction, like n morphisms, for instance, show up n times, right? In the level of each like underlying infinity groupoid or infinity one category, you can look at the n equivalences there, right? Versus the ones at the outer level that we've introduced. And completeness just makes sure that all of these kind of agree with one another, right? So we don't have duplicates. Okay. So the homotopy dimensions and category dimensions coincide. Right. Okay, so in this induction, I'm saying that complete zero-fold Segal spaces are con complexes. No one says that. Don't repeat that anywhere. I'm just doing this for the purposes of this talk. Yeah, don't tell the rest I said that. Nah, it's fine. So the idea today is that we're going to convert from a complete two-fold Segal space into a bicategory. That's our goal today. Okay. So what I want to do in order to do this is I'm going to show how to do this in a simpler case for a complete one-fold Segal space into a category. I'm going to present it in a way that I can generalize, and then I'm going to generalize it. That's the idea. So the first thing we're going to do is the n equals 1 case. And this is classical. This is due to Gurski in his 2001 paper, where a model for homotopy theory of homotopy theories, where he introduced complete Segal spaces. So this came with the definition, really. Okay. So theorem. So suppose that we have some complete Segal space. So is a complete Segal space space, i.e., that is to say, an infinity one category. Then the following data specifies a category, which I'm going to call H1 of X, the homotopy 1 category of our infinity 1 category. Okay, so what data do I need? Well, if we're going to write down a category, we should probably know what the objects are. And in that story that I told you earlier, the objects didn't change, did they? In a homotopy n category, the objects are exactly the same as the infinity n category. So we need to retrieve the objects from our infinity 1 category. What do? We look at our infinity 1 category at its underlying infinity groupoid, and then at the set of objects. Easy enough. So underlying infinity groupoid and the set of objects, or zero simplices, maybe you can say, if you got simplicial sets on the brain. Okay. So now, what are the Hom sets? Well, let's look back at how we obtained, okay, well, I guess, okay, not quite yet. Let's just look at this picture first. X1, remember, is in infinity one category. It's the infinity groupoid of one morphisms. X0 by X0 is the infinity groupoid of just pairs of objects, right? And what this map does is it just gives you the source and target, right? That's all it is. Okay. Let's suppose we picked out some particular objects, X and Y, right? If we take this pullback, we get what we might call the mapping space from X to Y. This is the infinity groupoid of morphisms starting at X and ending at Y, right? Now, I was being a little bit sneaky before. I threw reedy vibrancy in there, this mystical property. What reedy vibrancy does is it makes a lot of maps vibrations, including this one. This is actually a vibration. Therefore, this is a vibration in simplicial sets. A simplicial set where the map to the terminal object is a vibration, that's called a vibrant object. In fact, that's called a Kohn complex. So this thing here is a Kohn complex, a genuine infinity groupoid. And so with that in mind, when we want to look at the Homs from X to Y, all we're going to do, as expected with the homotopy category of infinity one category, is we take path components of one morphisms. That's what we do. The paths in this are going to be two morphisms between the one morphisms from X to Y, right? So we take path components. And what's nice, by the way, is that because this is a Kohn complex, pi 0 is not doing zigzag, chains in the simplicial set. It's just there is a morphism, right? So it's not too hard to deal with if you actually wanted to get into a particular infinity one category, right? So everything that I've said so far is just very, very classical. But I want to present the next step slightly differently. This is the bit where we tweak it a bit just so that it can generalize nicely. Okay, and that step is composition. So let's look at our Segal maps again. In particular, Segal maps level 2. This thing here, infinity groupoid of chains of length 2 together with a composite. Here, this is infinity groupoid of just chains of length 2 without any particular composite. This is a trivial vibration. And we can assemble from this a nice lifting problem in model categories. Again, I don't know if anyone here hasn't seen model categories before, but if you haven't, the calculus of model categories is to turn everything into liftings, to lift along vibrations. And there was there's a lot of results that show that this is kind of sufficient to do a lot of homotopy theory. So we're going to do just that. We're going to solve a lifting problem. This is actually already a lifting problem. Everything is cofibrant in simplicial sets. And this is a trivial vibration. So we can solve this lifting problem, right? We call this mu2. And then we have a map here from x2 to x1. Again, where this map identifies the particular composite. So this whole chain going up diagonally and then across, you start with a chain of two morphisms. I should have mentioned that this is the identity, but you start with a chain of two morphisms. You go up into the fiber above that chain and find a composite, and then you just extract the composite, right? So that's all we're doing, right? We have a fiber bundle and we have a section basically of the fiber bundle. That's what this is. It's not actually a fiber bundle, it's just a trivial vibration, a bit weaker, but same sort of idea. All right, now we take this whole picture, and this whole picture lives over x0 cubed, right? The starting object, the middle object, and the last object. We can fiber this whole thing over 3 objects, x, y, and z. We don't need that. Living in x0 cubed. And what do we get in the end? We get a map from x, y times x, y, z to x. What I'm going to just quickly write as x2 and then just like a superscript x, y, and z, just to say it's fibered over those 3. It's just the chains with a composite where everything's x, y, and z. And then we get this going to x of xz, right? And this is our composition operation after we apply pi 0, right? Pi 0 commutes with products. It doesn't commute with general limits, but it does commute with products. So we do get a map from hom of xy times hom of yz to hom of xz. That's exactly our composition operation. Okay. And finally, just to quickly note how to do identities. You have a nice map from x0 to x1, the degeneracy map. You fiber this over an object. You get, for some x, you get a map into hom of xx after applying pi 0. And that's your identity, right? It identifies a particular element. Okay. I guess maybe to write this out for people who are writing stuff out, what I actually mean here is that pi 0 of x to pi 0 of x, right? Okay. So I claim that all of this data is sufficient to obtain a category. The objects, morphisms, composition, and identities forms a category. We have to prove that. But all I'm going to do today is associativity. I'm not going to talk about uniters today. I just want to show you the techniques, right? So let's do associativity. All right. Associativity is going to require us to not go only up to x2, but all the way up to x3. So let's have some chain of 3 morphisms. And let's have another nice lifting problem. Well, how can we phrase the 2 composition operations we're trying to compare? We're trying to compare this operation to this operation. Well, what I'm going to do is the following. We have 2 other induced lifting problems. So we obviously have this map down here. I'll just put nice pictures here, chains of length 3. X3 is chains of length 3 together with a full composite and a witness of that. But in the middle live smaller spaces. I'm going to write them like this. We have X, and then what I'll draw as this diagram. What this is precisely is 2 copies of x2 pulled back over x1. So this is actually x2 times x1, x2, right? And what this is it's the space of chains of length 3 together with a composite of the first 2 morphisms and then a composite of that with the last morphism. Now, my mu2s that I told you about before, I can take a pullback of those as well, and I get a God-given solution to this lifting problem. I get a map here. This actually also turns out to be a trivial fibration, and this turns out to be a trivial fibration quite nicely. This is a lifting problem. I get a God-given solution by combining my mu2 operations from before. What I do is I have my chain of 3 morphisms. I apply mu2 once to compose the first 2 morphisms, and then I take the composite, and I apply mu2 again to compose that with the last morphism, right? And then there's this here. All right. And if you follow this whole diagram through, that chain from 3 arrows all the way just to 1 arrow, that's exactly the composition operation you get. If you fiber it over objects and apply pi 0, you get exactly the right composition operation. Okay. And the other way around, we have another space, which I'll write like this, which is again another pullback of 2x2s over x1, but in a different way. And I get another God-given solution to this lifting problem, because this is again a trivial fibration. I get another God-given solution to this lifting problem, right? Oh, it's really lagging. Given by composing the last 2 morphisms with mu2 once, then compose that with the other morphism with mu2. And if you follow this path now, we exactly get the other composition operation, compose the last two and then the first one. Okay. Now, what I'm going to do with these two is now, if we look here, I have another lifting problem, right? I've got a cofibrant thing, and I've got a trivial fibration. And I'm going to solve this lifting problem. I could just find a solution. It doesn't matter which one. And I can also solve this lifting problem. Doesn't matter what solution I choose, just solve it again. And if you look at this diagram, as it turns out, if you follow this and then go here, that's exactly the first composition operation again, because everything commutes. And if you follow this one, that's exactly the other composition operation, because everything commutes. So what I've done here is I've taken my two composition operations and I've realized them as solutions to this lifting problem. So same thing again here, and then x1. I've realized them as two solutions to this lifting problem. If you fiber this whole thing over objects and apply pi0, you will get precisely the two original composition operations of the different bracketings. It is a classical result of model category theory that if you have two solutions to the same lifting problem, there is a homotopy between them, always. And you get to choose what you mean by homotopy in general. What this gives us, if we then take this homotopy, so we'll get some homotopy between these. And if we take this homotopy, we fiber everything over objects nicely, we'll get this diagram, xy times xyz times xza. The alphabet is now cyclic, and xa. We get these two different composition operations by doing this or doing that. And we get a homotopy between these. Now, pi0, what would pi0 do to a homotopy? Well, what is a homotopy but a generalized path? So it will turn homotopies into equalities. When you apply pi0, any two maps that are homotopic will become equal. And so these two operations, after applying pi0, will be equal. And therefore, we have associativity. The two operations are equal up to some homotopy. And because I'm only proving associativity, that's all I need. Great. Okay, well, that's nothing particularly new. This is just what you do at level 1. That's very classical. But the nice thing is that when we start looking at homotopy bicategories, level H2, I actually don't even need to write anything new. I can actually just go all the way back up here and just edit what I've written already. So let's do that. So theorem again, theorem 2 this time. Suppose now we don't have a functor from delta op to set, but from delta op squared to set. I've just pulled the delta op out, so I've got just hom tensor. This is a complete two-fold Segal space now, i.e. an infinity 2 category. Suppose we have this. Then I claim the following data will specify a bicategory H2 of X, the homotopy bicategory of an infinity 2 category. All right, well, let's look at what we already have. If you take an infinity 2 category, take its homotopy bicategory, the object should be exactly the same. Well, okay, we can just do the same thing again. Let's just extract the objects. Well, x0 now is the underlying infinity 1 category now, right? x00 is now the underlying infinity groupoid. So we have to go one level further. x000, right? Underlying infinity 1 category, underlying infinity groupoid, set of objects. Okay. Now for the hom categories, I actually don't need to change anything. This is already correct. x1 now is the infinity 1 category of 1 morphisms. x0 times x0 is the underlying infinity one category times itself, right? So just pairs of objects. This map here is also a fibration in a suitable sense. And so what I get is that this thing is fibrant in the model structure for complete Segal spaces. And what that will mean is actually that this is an infinity one category itself. Right? So now when I look at the Hom categories, I'm perfectly entitled to take the homotopy category of the mapping infinity one category, right? The objects of this will be one morphisms from X to Y, and the morphisms in this will be path components of two morphisms, i.e. two morphisms up to invertible three morphisms. Okay. Now let's look at composition. Now I need to change even less. Already we have the infinity one category of compositions and infinity one category of chains of length 2. This whole thing is already a lifting problem. Every complete Segal space is cofibrant in the appropriate model structure. And this is already a trivial fibration in that model structure. So we can solve this lifting problem and we get some functor, some infinity one functor for composition, right? We fiber this over our objects. This is now a diagram in complete Segal spaces. And this time we apply H1. You have to prove that H1 preserves products. It does. Not just up to equivalence, but up to a canonical isomorphism of categories. So yeah, easy. And it's because pi0 does. All right. And now identities are very simple as well. We just put H1 here now. All right. But now the statement of the theorem isn't done because associativity, we no longer have the condition of associativity. We have the structure of an associator. So I'm going to get rid of this. And I'm going to talk about getting the associators now. And because I said nothing about proving identities before, I'm just going to show you the associators and not the uniters. All right. So let's look at this diagram. Well, once again, this is now just a diagram in infinity one categories, right? This still, everything here still works. So I can get this diagram again. There will be some homotopy here, right? And the way that I'm going to choose to represent homotopies is perhaps a bit peculiar. I'm going to use something called the classifying diagram. So there's a functor. So like in many notions of higher category, there's a way to embed categories into your notion. This is the most natural way for complete Segal spaces. This is a functor from cat to complete Segal spaces. I won't say too much about what concretely this is, but it's kind of like the nerve. The important thing about n is that if you do H1 circ n, so you take the nerve, you get an infinity one category, you go back down, this is the identity, right? You get the same category back, right? Okay. So what we're going to do here is we're going to say that a homotopy is going to be written like this. A homotopy between two maps will be written, so in the following way. We'll have perhaps some A, and we're going to do them kind of like cylinders. So we're going to have nerve of what I'll call I of 1. This is the walking category. What it is a category with two objects and an isomorphism between them. That's it, right? This is what we are going to mean by a homotopy. And for the model category theory, this is an appropriate notion of homotopy. It's totally fine, right? So if we have two solutions to a lifting problem, complete Segal spaces, we will obtain a map like this, where when you restrict to 0 or 1 in the walking category here, you'll get the two solutions to the lifting problem, right? That's our notion of homotopy. So what we'll get in the end for this picture is, if I just maybe get rid of this so that I can draw the homotopy as is. It's really slowing down now. We'll have times n of I of 1 to x of xa, right? And this homotopy, if we now hit this instead of with pi0, we hit this with h1. Now notice h1 commutes with products and it cancels out n. So now this will be a functor from something times I of 1 to something else. What is that but a natural isomorphism? a functor from C times I of 1 to D is exactly a natural isomorphism. Usually you see it in the sort of tensored version, in the sort of the opposite way, D I of 1, right? You send each object in C to an isomorphism in D, and you do this naturally, right? That's the usual notion of a natural isomorphism, but this is totally fine too, right? So what happens is that H1 will send this homotopy to an isomorphism, the associator, right? Okay. So we now have our associators, and you can get unitors in a similar way. All right. Now I need to prove that this thing actually is a bicategory. So to prove this, I need to prove the pentagon condition. How am I going to do that? Well, there's a reasonable amount to draw. So I'm going to be a little bit lazy and hop outside to another drawing that I've got, something that I prepared earlier. Hopefully this is the correct thing. Sometimes it hops around. Yep, exactly this. Right. So let's look at this drawing for a little bit and just stare at it. If we jump instead from X3 all the way up to level 4, so level 4 is now chains of 4 morphisms together with composites. We have all of these spaces living underneath, right? Let's look at one of these. This one right here is the space of chains of 4 morphisms together with a composite of the first 2 morphisms, the second 2, and then that with the last, right? The one living just above it is this one, right? Here we have a 2 simplex and a 3 simplex. Here we can see this kind of like this, right? We have possible composites in here with homotopies between them, and then that composed with the last thing, right? So if we look at this whole diagram, we will have God-given solutions to all of these lifting problems given by composing our composition operations from before. Our associators will also give us God-given solutions. Well, yeah, we get solutions that can map all the way up there. We can lift everything up to X4 as we did before. And what we're going to get in the end is this diagram. What's going on here? Well, we could lift all of our God-given solutions to the bottom level lifting problems all the way up to X4. These red arrows, those are all of our composition operations. Now, there are homotopies between these because they're solutions to the same lifting problem, but we have God-given homotopies by our associators, the homotopies we chose at the beginning at level 3, right? We can stick those together, and we get 2 different homotopies by concatenating these homotopies from this composition to that composition, right? The thing is that the way that you obtain a homotopy between 2 solutions of the same lifting problem is you turn those 2 solutions into a new lifting problem, the solution of which is your homotopy. These 2 paths of homotopies are thus solutions to another lifting problem, and so there must be a homotopy between them. There must be a 2 homotopy between homotopies. The way that I write these is literally just a map from A times ni of 1 times ni of 1 again, such that the vertical maps have to be identities, so it's globular. If you apply H1 to something like this, to this 2 homotopy, this blue thing in the middle, you'll get a map from A times I of 1 squared to B, where the vertical isomorphisms have to be identities. And what is this but an equality between functors? Thus, what happens in the end is that these 2 chains, H1 will map them to the 2 chains of 2 isomorphisms that are the pentagon condition, and it will map this 2 homotopy to an equality between those 2 chains. And thus the pentagon condition is proven. In general, we should expect associators, unitors, pentagonators, and higher coherence isomorphisms to show up as filling in holes between solutions to lifting problems in this way. I suspect that all the algebraic data of higher category theory that we usually get can be obtained in similar means by looking at chosen solutions or chosen sections to trivial fibrations, homotopies between them ad infinitum. And so that was the sort of structure that I wanted to show you today. And with that, I think I'll end my talk. So thank you very much for listening, everybody, and I'll take questions if there are any.
Yeah, let's give Jack a quick round of applause for wonderful talk. Thank you, Jack.
Thank you for inviting me.
And right, if there are any questions, so I'll leave the recording on for now. So if there's any questions, people want to be on the recording, feel free to ask them.
So I guess I'm kind of wondering, like, is there like a generalization to higher n for this? Because I'm understanding that, okay, this kind of bicategory, I mean, going to tricategories and stuff, that things get more messy. Like, for example, the Campbell's stuff only works, I think, for bicategories and not higher. So, like, can you say anything about that?
Yeah, right. So, I mean, work in progress, basically. But the thing is, I mean, yes, it will. I mean, it will get more complicated, but I mean, that's down to what model of n category you're using, and if that itself is already kind of complicated. I mean, these sort of solutions to lifting problems, I suspect things like Trimble n categories might be a nice way to sort of get sort of general homotopy n categories, but you're kind of like looking for actions of operads, and you could solve lifting problems where you're like filling in boundaries of associahedra or something like this repeatedly. And so that way you could obtain some sort of, you know, from the trivial fibration, like some sort of operad action, basically. And for like maybe Batanin and Leinster style things, you maybe want some sort of formulaic way to translate like pasting diagrams and whatever, you know, maybe computads into pictures of higher homotopies like this. And if you could do something like that, then just like filling in lifting problems kind of gives you all of your coherence conditions. So this is an active thing that I am thinking about right now. So if anyone is interested in helping me out with that or thinking about it with me, then please do give me a message. So yeah.
And would you like what kind of model for infinity n would you use? Would you like go for n-fold kind of a complete Segal things, or like is a kind of Cartesian property useful for this, like because now complete Segal space, that's Cartesian, whereas say twofold is no longer Cartesian. So like is there any problems with that?
I haven't thought about whether Cartesianness would help, but maybe it would. Theta n spaces might be a smarter place to go in that case, because those are Cartesian.
Yeah, or like even say complete Segal objects for in theta 2, so that would be like maybe more analogous sort of a thing.
Yeah, sure, right. I mean, the reason that I chose complete n-fold Segal spaces is because I've got a bit of an eye towards applying this to TQFT stuff, where things are formulated in complete n-fold Segal spaces. Obviously, those aren't always really vibrant, but that can be fixed. So, I mean, that was my motivation for choosing this specific model. But as you say, maybe there are more appropriate generalizations that have nicer technical properties for this construction. But yeah, I would think maybe like theta n, or yeah, these other things that you mentioned might be a good path forward.
Yeah, so maybe useful because towards the end you were talking about these categorical homotopies. So because that's the notion of homotopy for these complete Segal spaces, and in my work, like not yet published, I've generalized that notion to like any kind of a theta of any Cartesian model structure. So maybe that's useful.
Yeah. Okay. Yeah. Yeah. Maybe we should talk about that. That sounds really nice. Okay. Cool. Awesome. Yeah. Thank you.
Right. So maybe I'll stop the recording.
Yeah. If anyone else has questions, feel free to email me or send me a message or whatever. So.